Domino's doesn't just make pizza, it mass produces millions of them with military precision. Behind the scenes, giant machines mix dough by the ton, sauce is pumped through industrial lines, and toppings are added at lightning speed. In this documentary, we take you inside the factory to reveal how Domino's pizzas are really made, and the insane process that keeps the world fed one slice at a time. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough-making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal, high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers. and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand-stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sourced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly. From the final stage of yeast fermentation, steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixes are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. The journey of McDonald's French fries begins long before they reach the restaurant kitchens. It all starts with the careful selection and cultivation of the perfect potatoes. Every fry that ends up in a McDonald's restaurant has been through a rigorous process, ensuring consistency in taste, texture, and appearance. The company relies on specific varieties of potatoes, primarily the Russet Burbank, Russet Ranger, Umatilla Russet, and Shepherdie. These potatoes are chosen for their high starch content, which helps create that signature crispy exterior and fluffy interior when fried. They are also selected for their long, uniform shape, which allows McDonald's fries to be consistently straight and evenly sized. Farmers who grow potatoes for McDonald's work under strict guidelines to meet the company's high standards. The soil must be rich in nutrients, well drained, and have the right pH levels to support optimal potato growth. Before planting even begins, farmers carefully prepare the land. The soil is tilled and aerated to improve its structure, allowing the roots of the potatoes to spread evenly. Proper soil preparation ensures that the potatoes will grow uniformly in size and shape, which is crucial for creating the perfect fries. Once the soil is ready, seed potatoes are selected. These are not actual seeds, but small, specially chosen potato tubers that will sprout and grow into full-sized potato plants. Farmers cut these seed potatoes into pieces, making sure each piece contains at least 1 or 2 eyes, the spots where new growth will emerge. These seed pieces are then treated with an antimicrobial solution to prevent disease and are left to cure for a short period before being planted. When the conditions are right, typically in early spring, the seed potatoes are planted in long, evenly spaced rows using precision planting machines. These machines ensure that each seed piece is placed at a consistent depth and distance from the others. Consistent spacing allows the plants to develop evenly, preventing competition for nutrients and ensuring that each potato grows to an optimal size. As the potato plants grow, they require constant monitoring and care. Farmers use irrigation systems to provide a controlled amount of water, ensuring that the plants receive enough moisture without becoming waterlogged. Too much water can lead to rot, while too little can cause the potatoes to develop poorly. Advanced irrigation systems, including center pivot sprinklers and drip irrigation, help maintain the perfect balance. Pest control is another crucial factor. Farmers use integrated pest management techniques, which combine natural predators, crop rotation, and selective pesticide application to keep harmful insects at bay. Keeping pests under control prevents damage to the potatoes and reduces the need for excessive chemical treatments. Throughout the growing season, McDonald's suppliers test the potatoes for starch content, sugar levels, and overall quality. These tests help ensure that the potatoes are developing the ideal characteristics for frying. Potatoes with too much sugar will turn dark when fried, while those with too little starch won't develop the crispy texture that McDonald's fries are known for. When the potatoes reach maturity, typically after 90 to 120 days, the leaves and stems of the plants begin to wither and die. This signals that the potatoes underground are ready for harvest. However, before harvesting begins, farmers often use a technique called vine desiccation. This involves cutting or chemically drying the potato vines to toughen the skins of the potatoes and make them more resistant to damage during harvesting. Harvesting is done using specialized potato harvesters. These machines carefully dig into the soil, lifting the potatoes while shaking off excess dirt. The potatoes are then conveyed into large storage bins or directly into trucks for transport. To minimize bruising and damage, the harvesters are designed to handle the potatoes gently, using soft conveyor belts and cushioned drops. Once harvested, the potatoes undergo a crucial curing process. This involves storing them in temperature and humidity-controlled environments for several weeks. The curing process allows minor cuts and bruises to heal and strengthens the skins, improving their storage life. During this time, the potatoes are kept at a carefully maintained temperature, typically between 45 degrees Fahrenheit and 50 degrees Fahrenheit, to prevent sprouting and spoilage. After curing, the potatoes are stored in massive, climate-controlled storage facilities. These storage units can hold millions of pounds of potatoes and are designed to keep them in optimal condition for months. Proper ventilation is key, as too much humidity can cause mold and rot, while overly dry conditions can cause the potatoes to shrivel. Before the potatoes are transported to processing facilities, they undergo another round of quality control. Samples are taken and tested for defects, size consistency, starch content, and sugar levels. Any potatoes that don't meet McDonald's strict standards are either sent for use in other food products or discarded. Only the best potatoes make it through to the next stage of the process. Now that the potatoes have been grown, harvested, cured, and stored, they are ready for transport to the processing facilities, where they will be transformed into the famous McDonald's fries. Specialized trucks equipped with temperature control systems transport the potatoes to ensure that they remain in perfect condition during transit. The logistics of transporting millions of pounds of potatoes require precise planning to ensure a steady supply of raw materials to processing plants. Upon arrival at the processing facility, the potatoes are unloaded and undergo an extensive inspection process. Workers and automated scanning systems check for any potatoes that might have developed defects during storage or transport. Any potatoes that fail the inspection are removed from the production line. The selected potatoes are then sent into the processing area, where the transformation into fries begins. The next step in the process is cleaning. The potatoes are loaded onto conveyor belts and passed through a series of high-pressure washers and rotating scrubbers. These machines use powerful jets of water and mechanical brushes to remove any remaining dirt, debris, and residual pesticides. The goal is to ensure that the potatoes are completely clean before they are peeled and cut. Once cleaned, the potatoes are sent to industrial steam peelers. These machines use high-pressure steam to loosen the potato skins, making them easy to remove. The potatoes are then tumbled in rotating drums, where the loosened skins are gently rubbed away. This method of peeling is highly efficient and helps preserve as much of the potato as possible, minimizing waste. After peeling, the potatoes pass through another round of inspection. Advanced optical sorting machines use cameras and sensors to detect any remaining imperfections. If a potato has a blemish or an area of discoloration, the machine automatically removes it from the production line. This ensures that only high-quality potatoes continue to the next stage. Now that the potatoes are cleaned, peeled, and inspected, they are ready to be cut into the familiar fry shape. Industrial cutting machines use high-speed water knives to slice the potatoes with incredible precision. These machines use pressurized water jets to push the potatoes through razor-sharp blades at speeds of up to 117 miles per hour. The result is perfectly uniform fries, ensuring consistency in size and shape across every McDonald's location. After being cut, the fries are rinsed in cold water to remove excess surface starch. This step is essential because too much starch can cause the fries to clump together and fry unevenly. By rinsing away the surface starch, the fries maintain their individual shape and crispiness after cooking. Once rinsed, the fries move on to the next critical step in the process: blanching. Blanching is a partially cooking method that helps preserve the fries' texture, color, and flavor. The fries are briefly submerged in hot water at a precisely controlled temperature, which removes additional sugars and further improves the final texture. This step also ensures that the fries achieve their signature golden color when cooked. Now that the potatoes have been washed, peeled, cut, and blanched, the next critical step in their transformation into McDonald's French fries is the drying process. This stage is essential because excess moisture can interfere with the frying process, preventing the fries from achieving the crispy texture that customers expect. After blanching, the fries emerge wet with a thin layer of surface moisture. If this moisture isn't removed, it will cause the fries to absorb too much oil during frying, resulting in a greasy, soggy texture instead of the signature crispiness. To prevent this, the fries are conveyed into an industrial drying system. These drying machines use high-powered air blowers to remove excess water from the surface of the fries. As the fries move along a conveyor belt, large fans blow heated air over them, gradually evaporating the remaining moisture. The temperature and speed of the drying process are carefully controlled, as drying too quickly can cause the fries to develop an uneven texture, while drying too slowly can lead to unwanted starch gelatinization. To ensure consistency, infrared sensors monitor the moisture content of the fries in real time. If any fries still contain too much moisture after passing through the first drying phase, they may be sent through an additional round of drying before moving forward. This step ensures that every fry is prepared correctly before it reaches the frying stage. Once the fries have been properly dried, they are ready for the first round of frying, known as par frying. This is a crucial step in the McDonald's fry making process, as it sets up the fries for their final cooking once they reach restaurant kitchens. During par frying, the fries are submerged in a carefully maintained blend of oils, which typically includes a mix of canola, soybean, and hydrogenated soybean oils. The oil blend is formulated to provide the ideal balance of flavor, crispiness, and shelf stability. Maintaining the right frying temperature is critical. The oil is heated to approximately 335 degrees Fahrenheit, ensuring that the exterior of the fry sets properly without overcooking the interior. The fries are only in the oil for about 45 to 60 seconds, just long enough for their exterior to begin forming a crisp, golden shell. At this stage, the inside of the fry remains mostly uncooked. The goal of par frying is not to fully cook the fries, but rather to create a stable, structured outer layer that will crisp up perfectly when they are fried a second time in McDonald's kitchens. As the fries move through the fryer, automated stirring mechanisms ensure that they cook evenly. The machines continuously adjust frying times and temperatures based on real-time data collected by sensors in the oil. These sensors monitor changes in oil quality, ensuring that the fries cook consistently and that the oil remains fresh throughout the production process. To maintain oil quality, the frying system is equipped with an automatic filtration system that continuously removes food particles and debris. This prevents burn particles from affecting the taste and color of the fries, ensuring that each batch is cooked under optimal conditions. Additionally, the used oil is periodically replaced to maintain consistency and prevent the fries from absorbing any off flavors. Once the fries have been par fried, they must be cooled quickly to prepare them for freezing. The rapid cooling process prevents overcooking and locks in their texture and flavor. As they exit the fryer, the fries are conveyed through a cooling tunnel where cold air is blasted onto them. This brings their temperature down rapidly, stopping the cooking process before they move on to the freezing stage. Now the fries are ready for individual quick freezing, a process that ensures they remain fresh and retain their texture during transportation and storage. Unlike traditional freezing methods, which can cause ice crystals to form and damage the structure of the fries, IQF rapidly freezes each fry in just seconds, preventing clumping and preserving the ideal texture. As the fries move through the freezing tunnel, they are kept in constant motion to prevent them from sticking together. This ensures that when they are later packaged, they remain separate and can be easily portioned at McDonald's restaurants. The IQF process is one of the most important steps in the production of McDonald's fries, as it allows the fries to maintain their signature quality even after being stored and transported over long distances. Without this rapid freezing process, the texture and flavor of the fries would degrade before they ever reach the restaurants. Now that the fries are frozen, they are ready for packaging. The frozen fries are conveyed to the packaging area, where they are portioned into pre-measured bags. The packaging process is highly automated, ensuring precision and consistency. As the fries enter the packaging machines, they pass through electronic weighing systems that measure out the correct amount for each bag. The machines are programmed to fill bags of different sizes, depending on whether they are destined for restaurants or retail sales. Once the correct amount of fries has been portioned, the packaging machine seals the bags using airtight, food-safe plastic. The sealing process is crucial as it prevents moisture and air from reaching the fries, which could cause freezer burn or spoilage. Each bag is then labeled with information such as batch numbers, expiration dates, and storage instructions. These labels ensure that the fries can be tracked throughout the supply chain and that restaurant staff know how to handle them properly. With the fries now packaged, they are moved to storage freezers, where they remain at sub-zero temperatures until they are ready to be shipped to McDonald's locations worldwide. These massive freezers are designed to keep the fries at a stable temperature, preventing fluctuations that could affect their quality. To maintain efficiency, McDonald's employs a sophisticated inventory management system that tracks the movement of frozen fries from production facilities to distribution centers and, ultimately, to individual restaurants. This system ensures that restaurants always receive fresh shipments and that the fries are used in a first-in, first-out manner to prevent older stock from lingering in storage. Now that the McDonald's fries have been frozen and packaged, the next critical step is their transportation and storage. Ensuring that the fries maintain their quality from the factory to McDonald's restaurants worldwide requires a highly coordinated logistics system. Every detail, from temperature control to packaging integrity, must be carefully managed to prevent any compromise in taste, texture, or safety. Once the fries are sealed in airtight bags and labeled, they are transferred into large freezer storage facilities within the processing plant. These storage freezers maintain a consistent temperature of around -18 degrees Celsius or lower, preventing ice crystal formation, which can degrade the fries' texture. The storage rooms are equipped with high-efficiency cooling systems that circulate air evenly, ensuring that no section of the storage area fluctuates in temperature. Inside these freezers, the fries are stacked onto pallets, which hold multiple cases of packaged fries. Each pallet is organized based on batch numbers and production dates, ensuring that inventory follows a first-in, first-out rotation. This method ensures that the oldest batches are always shipped out first, preventing any fries from sitting in storage for too long. Once ready for distribution, the pallets of frozen fries are loaded onto refrigerated trucks. These trucks, known as reefers, are specially designed to transport perishable goods over long distances without breaking the cold chain. Before loading, drivers and logistics personnel conduct a thorough inspection of the truck's refrigeration system to ensure that it maintains the required sub-zero temperatures throughout the journey. As the fries are transferred from the freezer storage to the trucks, time is of the essence. The fries must remain frozen at all times, so the loading process is highly efficient. Warehouse workers use forklifts to move entire pallets of fries onto the trucks in a carefully coordinated sequence. The doors of the truck are kept closed for as long as possible to prevent warm air from entering. And once loading is complete, the truck's refrigeration system is double-checked before departure. Throughout the transportation process, temperature sensors continuously monitor conditions inside the truck. These sensors send real-time data to logistics teams, who can track the temperature remotely and intervene if any issues arise. If the temperature rises even slightly above the acceptable range, alarms notify the driver and logistics managers so that corrective actions can be taken immediately. McDonald's fries travel through an intricate global supply chain, often covering thousands of miles before reaching their final destination. Some shipments are sent directly to regional distribution centers, while others may be shipped overseas using refrigerated cargo containers. In the case of international shipments, frozen fries are loaded into specialized shipping containers equipped with advanced cooling units. These containers ensure that the fries remain at the proper temperature even during extended voyages across oceans. Once the fries arrive at a McDonald's distribution center, they are unloaded and immediately placed into cold storage warehouses. These facilities operate similarly to the freezer storage in processing plants, maintaining sub-zero temperatures and using the FIFO inventory system. The fries remain in these distribution centers until they are scheduled for delivery to specific McDonald's restaurants. At this stage, delivery trucks equipped with refrigeration units transport the fries from the distribution centers to individual McDonald's locations. These trucks are designed for short-haul deliveries, ensuring that the fries remain frozen while en route to the restaurants. The loading and unloading process is again handled with precision, minimizing exposure to warm air to maintain the fries' frozen state. When the fries arrive at a McDonald's restaurant, they are immediately placed into a walk-in freezer. These freezers, located in the back of the kitchen, are maintained at a constant temperature of -18 degrees Celsius or lower. McDonald's staff follow strict protocols when handling frozen fries, ensuring that the cold chain remains intact. To manage inventory efficiently, McDonald's employees use a stock rotation system that ensures older batches are used first. Staff are trained to check expiration dates and packaging integrity before moving fries from the freezer to the cooking area. If any package shows signs of damage or thawing, it is discarded to maintain quality and safety standards. With the fries safely stored in McDonald's freezers, the next stage of the process begins: preparation and cooking. When an order for fries is placed, restaurant staff retrieve a bag of frozen fries from the freezer and transfer it to the fry station. The fry station is equipped with multiple deep fryers, each filled with a specially formulated blend of oils that have been carefully designed to give McDonald's fries their signature taste and texture. Before frying, the fries are measured out using a portioning system that ensures consistency across all orders. This portioning system dispenses the correct amount of fries into a stainless steel fry basket, preventing over or under portioning. Consistency is a crucial factor in McDonald's operations, ensuring that every customer receives the same high-quality product, whether they are ordering fries in New York, Tokyo, or London. Once portioned, the fries are submerged into the hot oil, which is maintained at a precise temperature of around 345 degrees Fahrenheit. The restaurant fryers are equipped with built-in temperature sensors that continuously monitor the oil and make automatic adjustments to keep it at the optimal frying temperature. If the oil becomes too hot, the fries can burn and develop an unpleasant taste. If the oil is too cool, the fries will absorb too much oil, becoming greasy and soggy. The frying process typically lasts for approximately 3 minutes, during which time the fries undergo a dramatic transformation. The high temperature causes the moisture inside the fries to rapidly turn into steam, creating the crispy outer layer that defines McDonald's fries. Meanwhile, the starches inside the fry undergo gelatinization, giving the interior its signature fluffy texture. To ensure even frying, McDonald's fryers use automated timers and shaking mechanisms that periodically agitate the fry baskets. This prevents the fries from clumping together and ensures that every fry is cooked to perfection. Once the fries have finished frying, the baskets automatically rise out of the oil, allowing excess oil to drain. At this point, the fries are still extremely hot and must be handled with care. They are immediately transferred to a stainless steel holding tray, where they are given their final touch, seasoning. McDonald's fries are seasoned with a precise amount of salt, which is evenly distributed using a specialized shaker. The amount of salt added is carefully calibrated to ensure that every fry has the same level of seasoning. Too much salt can overwhelm the delicate flavor, while too little can leave the fries tasting bland. The fries are then transferred to their final serving containers, whether that be a small, medium, or large fry box. McDonald's packaging is designed to retain heat while allowing some airflow to prevent the fries from becoming soggy. The packaging process is also highly standardized, ensuring that every order looks and feels the same. Ensuring that every McDonald's fry meets the company's exacting standards requires an extensive quality control process at every stage of production. From farm to fryer, each step is carefully monitored and tested to maintain consistency in taste, texture, and appearance. These rigorous quality control measures are essential in producing fries that are identical in every McDonald's restaurant worldwide. It all begins at the potato farms, where McDonald's agronomists work closely with farmers to oversee crop development. Soil conditions, irrigation levels, and growing techniques are constantly evaluated to ensure that the potatoes develop the right starch content and texture for frying. Once harvested, samples from each batch are tested for size, shape, sugar content, and moisture levels. Only potatoes that meet McDonald's specifications are approved for processing. At the processing facility, automated optical sorters inspect the potatoes before they enter production. These machines use advanced imaging technology to detect any imperfections such as bruising, rot, or irregular shapes. Any potato that does not meet quality standards is removed from the line. As the potatoes move through peeling, cutting, blanching, and drying, additional checks ensure that each fry maintains the correct dimensions, moisture balance, and uniformity. One of the most critical quality control steps occurs during par frying. Sensors in the fryers constantly measure oil temperature and frying time to ensure that the fries develop the correct texture and color. Samples from each batch are taken and tested for oil absorption, crispness, and interior fluffiness. If any deviations are detected, adjustments are made to the frying parameters to maintain consistency. Once the fries are frozen, further inspections take place. Random samples are pulled from production batches and tested in lab conditions to ensure that freezing has not affected their texture or flavor. Fries are fried, tasted, and measured for crispiness, color, and moisture retention. Any irregularities result in adjustments to processing equipment or procedures. During transportation, strict temperature monitoring ensures that the fries remain frozen at all times. Sensors in refrigerated trucks and shipping containers provide real-time temperature data, ensuring that any fluctuations are immediately addressed. If a shipment experiences even minor temperature inconsistencies, it may be rejected to prevent compromised product quality. Upon arrival at McDonald's restaurants, employees perform additional checks before storing the fries in freezers. Staff are trained to inspect packaging for any signs of damage or thawing. When preparing fries for customers, they follow precise cooking procedures, including setting timers, checking oil temperatures, and following strict portioning and seasoning guidelines. To further ensure quality, McDonald's conducts random in-store testing. Quality control specialists visit restaurants to sample fries and evaluate their texture, taste, and temperature. These evaluations help identify any potential issues in the cooking process. ensuring that customers receive the perfect fries every time. It all begins with the careful sourcing and intake of raw chicken, a process that is both biologically sensitive and highly mechanized to maintain consistent quality and food safety. The chickens destined for KFC facilities are selected from specific poultry farms that follow stringent guidelines set by both KFC's corporate standards and local regulatory bodies. These farms raise broiler chickens, a breed specifically developed for rapid growth and high meat yield, particularly in the breast and thigh areas. To ensure consistency in texture and flavor, the birds are typically grown under controlled feeding regimens with strict monitoring of their diet, environment, and health status from hatchery to harvest. Once the birds reach the appropriate weight and age, usually between 5 to 7 weeks, they are transported live in temperature-regulated, well-ventilated trucks to the processing facility. Upon arrival, the birds are unloaded through an automated conveyor system and transferred to a staging area that uses dim lighting and gentle sound cues to keep the animals calm. This pre-processing environment is crucial for maintaining meat quality, as high stress can cause conditions like pale, soft, and exudative meat, or dark, firm, dry meat, which are both unsuitable for KFC's strict quality requirements. The first critical step in the factory is stunning, which is done using controlled atmosphere stunning, a method that introduces carbon dioxide in gradually increasing concentrations to render the chickens unconscious. This technique is widely considered more humane and helps preserve the quality of the meat. Once the birds are unconscious, they move to the next stage, where an automated system makes a precise incision to the neck, ensuring rapid and thorough bleeding. The bleeding process is closely timed and monitored using sensors and timers to maximize the efficiency of blood removal, which is essential not only for meat appearance and shelf life, but also for meeting food safety regulations. Following exsanguination, the birds proceed through a high-capacity scalding tank filled with water heated to approximately 60 degrees Celsius. This stage loosens the feathers by relaxing the collagen in the feather follicles. The duration and temperature are controlled to a fine margin to ensure that the skin is neither overcooked nor damaged. After scalding, the birds are transferred into rotary feather pluckers, drum-shaped machines lined with soft rubber fingers that rotate at high speeds. These fingers remove feathers through a gentle abrasive action. Any residual feathers, particularly around the wings and tail, are removed by additional targeted plucking devices or hand finishing stations, depending on the processing line speed and factory setup. The next step is evisceration, a highly mechanized process involving robotic arms and vision-guided machinery. The system first makes a precise incision along the abdominal cavity before extracting the internal organs. This includes the heart, liver, gizzard, and intestines, which are separated into byproduct streams for different uses or disposal. Each carcass is inspected by high-speed cameras equipped with AI-powered image recognition software to detect any abnormalities such as bruising, discoloration, or contamination. Chickens that fail this inspection are automatically diverted from the production line for further examination or removal. This real-time quality assurance technology helps maintain a consistent and safe supply of chicken for further processing. Now it's time to move on to the chilling process, which is absolutely vital for halting bacterial growth and ensuring a clean transition from slaughter to further cutting and seasoning. KFC factories typically use an immersion chilling method, where eviscerated chickens are conveyed through long stainless steel tanks filled with chlorinated cold water, maintained at around 0 to 4 degrees Celsius. The flow of water is designed in a countercurrent pattern, meaning the cleanest water contacts the most recently added chickens, ensuring optimal hygiene. This step rapidly reduces the internal temperature of the chicken from roughly 40 degrees Celsius to below 4 degrees within an hour, thereby locking in freshness and significantly extending the shelf life of the meat. After chilling, the carcasses proceed to the cutting and portioning stage. This part of the process is perhaps one of the most intricate in the factory. Specialized rotary cutting machines equipped with lasers and 3D scanners assess the size and density of each chicken in real time. Based on this data, programmable robotic blades segment the carcasses into uniform cuts: legs, thighs, wings, breasts, and keels. Each piece is sized to match strict dimensional and weight criteria, which are crucial for ensuring consistent cooking times and presentation across all KFC restaurants worldwide. The system is calibrated to yield the optimal number of each type of piece from every bird, reducing waste and maximizing efficiency. If a cut doesn't meet the precise size range, it is automatically redirected for use in alternative products like tenders or popcorn chicken. The next phase focuses on marination, a process that introduces moisture, flavor, and functional ingredients into the chicken to enhance both taste and texture. Once portioned, the chicken pieces are loaded into massive stainless steel tumblers, each capable of holding hundreds of kilograms of product. Inside the tumbler, a proprietary liquid marinade blend is introduced. While the exact formulation is a closely guarded secret, the marinade typically includes salt, phosphate-based tenderizers, flavoring agents, and sometimes buttermilk solids to create the tender, juicy interior that KFC is known for. The tumbling action lasts anywhere from 15 to 30 minutes, depending on the batch size and desired intensity, and the drum rotates on multiple axes to ensure that every surface of every piece of chicken is exposed to the marinade. This mechanical agitation also helps the meat fibers absorb the liquid more thoroughly, contributing to the product's juiciness even after high temperature frying. But up next comes the breading stage, which is arguably the most iconic part of KFC's production process. After marination, the chicken is gently drained and transferred to the breading stations, where each piece is coated in the proprietary blend of flour and seasoning known famously as the 11 herbs and spices. To replicate the hand-breaded quality that KFC is known for, even at industrial scale, specialized breading drums are used. These drums simulate the hand-tossing action by gently rolling the chicken pieces in the seasoned flour, while pneumatic paddles and vibration systems ensure that every crevice is fully coated. At this point, moisture content is carefully controlled to ensure adhesion without creating clumps or overly moist surfaces, which would ruin the crispy texture during frying. Once breaded, the chicken moves immediately to the par frying or pre-frying stage. This step is critical for setting the breading so it doesn't fall off during full cooking at the restaurant. The breaded pieces are passed through continuous fryers filled with hot oil maintained at temperatures between 170 to 180 degrees Celsius. In this stage, the chicken is fried for a short duration, usually 90 to 120 seconds, just enough to solidify the coating and begin the Maillard reaction, which is responsible for the development of flavor and the golden color. The oil used in this step is filtered and refreshed continuously using an inline oil management system that maintains optimal frying conditions and ensures that the final product is never tainted by burnt residues or off flavors. The partially cooked chicken is then lifted out of the fryer via a conveyor system and deposited onto a draining belt that uses both gravity and air jets to remove excess oil. Now, it's time to transition to the flash freezing process. This is where partially cooked chicken is rapidly frozen to lock in all the flavors, textures, and moisture absorbed during marination and breading. Each piece is conveyed into a spiral freezer or impingement freezer, both of which use sub-zero air blasts or liquid nitrogen vapor to drop the temperature of the chicken from over 60 degrees Celsius to below -18 degrees in under 10 minutes. Rapid freezing is crucial to prevent the formation of large ice crystals, which can damage the cellular structure of the meat and result in dryness or texture loss after final cooking. During this process, each piece is also individually quick frozen, which prevents clumping and allows for precise portioning when packaging. The next step in the factory process is the automated packaging of the individually quick frozen, par-fried chicken pieces. a phase that combines high-speed precision machinery with meticulous control over product integrity. Once the chicken emerges from the spiral or impingement freezer, each piece is conveyed to a sophisticated vision inspection system that performs a final quality assurance check. High-resolution cameras and laser scanners examine each piece for uniform breading coverage, appropriate size, and the absence of any structural defects like broken bones or irregular shapes. Pieces that fail this inspection are removed from the line using targeted air jets and routed for rework or disposal, depending on factory protocol. Once the pieces pass inspection, they are conveyed into a portioning station where intelligent weighing and sorting systems group them into standardized sets that align with KFC's iconic bucket meal configurations. These could be 8-piece, 12-piece, or 16-piece configurations, depending on the regional product lineup. Multi-head weighing machines calculate the total weight and count of each portion, ensuring that every pack not only meets visual and compositional standards, but also falls within a narrowly defined weight range for inventory accuracy and consistent customer experience. These grouping systems operate at incredibly high speeds, hundreds of portions per minute, with tolerances as tight as +1 gram. Each portion of chicken pieces is then dropped into a form-fill seal machine or into pre-formed plastic pouches, depending on the final packaging format. The form-fill seal machines shape a plastic film into a bag, load it with chicken, flush it with a nitrogen-rich gas to minimize oxygen, and heat seal it in a continuous, uninterrupted process. Modified atmosphere packaging is used here to extend shelf life while preventing freezer burn or flavor degradation. The gas blend, often a mix of nitrogen and carbon dioxide, inhibits microbial growth and oxidation without adding any chemicals or preservatives. After sealing, the packages are labeled with all necessary tracking and compliance information. High-speed thermal transfer printers apply labels that contain lot numbers, plant codes, production timestamps, and freeze dates. These labels also include data matrix barcodes or QR codes used for traceability, allowing KFC's central quality control teams to trace every package back to its exact farm, batch, and processing line in the event of a recall or audit. Automated verification systems scan each label for accuracy and readability. Any incorrectly labeled packages are automatically rejected from the line and placed in a designated review bin for manual inspection. Now it's time to move on to case packing, where multiple individually sealed packs of chicken are grouped into corrugated cardboard boxes, each built to withstand long-distance cold chain transportation. Robotic arms equipped with vacuum suction grippers pick and place the sealed bags into the boxes with extreme precision, ensuring that space is maximized while maintaining the integrity of the chicken. Each case typically holds a specific number of meals or bucket configurations and is marked with a unique identifier. Once filled, the boxes are sealed using automated taping machines and pass through weight verification stations to ensure each box matches the expected load. Once packed, these boxes are stacked onto pallets using robotic palletizers. These robots follow pre-programmed stacking patterns that balance weight and maximize vertical space without compromising stability. Slip sheets and corner boards are often inserted between layers to protect the boxes during transit. Each completed pallet is then shrink wrapped using a rotary arm or turntable stretch wrapper, which encases the entire stack in several layers of industrial plastic film to secure the load for transportation. A final barcode label is applied to each pallet, integrating it into the warehouse management system, which tracks every movement of inventory from production to dispatch. Next comes the crucial cold storage phase. The finished pallets are transferred via automated guided vehicles or high-speed conveyor systems into a massive cold storage facility, maintained at a consistent temperature of -18 degrees Celsius or lower. These storage facilities are designed with energy efficiency and inventory management in mind, often featuring high bay racking systems and vertical lift modules that allow for dense, organized storage. Temperature and humidity are monitored continuously by sensors linked to a centralized control room, where technicians receive alerts if any deviations occur. These warehouses are often equipped with backup generators and emergency protocols to ensure uninterrupted refrigeration in the event of power failures. After sufficient time in cold storage, which may range from a few days to several weeks depending on demand, the frozen chicken pallets are scheduled for distribution. The dispatch process begins with a pick and pack phase, where orders from various KFC regional hubs or franchise warehouses are collated. Advanced logistics software optimizes which pallets to pull based on freshness, production date, and delivery location. Selected pallets are loaded onto refrigerated trailers that maintain a controlled environment throughout the entire journey. These trucks use insulated walls and powerful refrigeration units that can be monitored remotely to ensure temperature compliance from factory to franchise. As these trucks transport the frozen chicken to regional KFC distribution centers or directly to individual restaurants, the cold chain is never broken. The receiving locations are equipped with cold storage facilities of their own, ensuring the chicken remains at safe temperatures until it's needed. At this stage, each restaurant receives a specific allocation based on forecasted customer demand, which is calculated using advanced demand planning software linked to point-of-sale data and regional market trends. The chicken remains sealed until it's ready to be used in the restaurant's kitchen, where the final stages of cooking take place. But now it's time to dive into the heart of the KFC restaurant kitchen, where the transformation from pre-cooked frozen chicken into the hot, crispy, golden brown pieces we all recognize occurs. After thawing in temperature-controlled refrigeration units for a specific number of hours, typically overnight, the chicken is brought to the breading station. Though the chicken was par-fried and breaded at the factory, a second layer of fresh breading is applied in-store to create the distinctive double crunch texture KFC is famous for. This is where the Colonel's proprietary 11 herbs and spices come into play. Each restaurant receives sealed tubs of this secret seasoning blend, pre-measured and tamper-proof. The thawed chicken pieces are first dipped into a cold, seasoned egg wash or a specialized batter mix, depending on the region. Then, they are placed into large breading bins containing the flour and spice mixture. Trained team members follow a specific press and fold technique, which involves pressing the flour onto the surface of the chicken and folding it multiple times to ensure full adhesion and the formation of the characteristic craggy, crispy coating. Each piece is then gently shaken to remove excess breading and laid out on wire racks to rest before frying. This resting period is short but essential. It allows the coating to set and adhere to the surface of the meat, reducing slippage during frying. Next, the chicken is placed into large open fryers filled with high stability frying oil, often a soybean or canola blend, optimized for high temperatures and neutral taste. The fryers are preheated to exact temperatures, typically around 170 to 180 degrees Celsius, and the chicken is cooked under pressure for a controlled duration. KFC's use of pressure fryers is a distinctive element of its cooking process. The pressure cooking not only reduces cooking time, but also seals in moisture, ensuring the chicken remains juicy while achieving a perfectly crispy exterior. Sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration down to the second. Once the timer signals completion, the fryer basket lifts automatically and the cooked chicken is removed using heat-safe tools to ensure safety and hygiene. After frying, the chicken is transferred to heated holding cabinets that maintain a precise internal temperature, typically around 60 to 65 degrees Celsius, for a limited time, usually no longer than 90 minutes, to ensure optimal freshness and food safety. These cabinets are fitted with internal timers and alert systems to prompt kitchen staff when a batch is nearing the end of its holding time. Any product not sold within this window is discarded according to food safety protocols to maintain KFC standards. Now that the chicken is hot, crisp, and ready, it's portioned into the familiar red and white striped buckets. Each bucket is made from food-grade, grease-resistant cardboard, printed with high-resolution branding that remains vibrant, even under heat and oil exposure. The buckets are assembled on-site from flat pack form using pop and lock mechanisms and lined with waxed paper liners. The kitchen crew follows strict guidelines when arranging the pieces inside each bucket, ensuring an appealing visual mix of drums, thighs, wings, and breasts. The buckets are then sealed with fitted plastic or cardboard lids to retain heat and are either handed to walk-in customers or packed into thermal delivery bags for transport. The final stretch of the production process involves a complex web of quality assurance protocols, food safety audits, sustainability initiatives, and continual technological improvements, all of which are critical to ensuring that every KFC fried chicken bucket, whether purchased in Tokyo, New York, or Johannesburg, meets the same high standard of taste, appearance, and food safety. These behind-the-scenes systems may not be visible to the end consumer, but they represent the foundation of KFC's global manufacturing and supply chain model. One of the most rigorous systems in place is the Hazard Analysis and Critical Control Points, or HACCP, framework. This is applied across all phases of the production lifecycle, from live animal handling at the poultry farms to final packaging at the restaurant level. Every critical control point is identified, monitored, and logged digitally. For example, in the chilling process, sensors verify that the internal temperature of chicken pieces drops to below 4 degrees Celsius within a very specific time frame. If any batch fails to meet that requirement, the system will automatically flag the anomaly, prevent further processing, and isolate the affected lot until a manual inspection is completed. These digital controls are complemented by human oversight. Trained quality control technicians regularly inspect samples at random, visually assessing breeding adhesion, meat color, texture, and aroma. At the plant level, sanitation is treated as a mission-critical activity. Every line, blade, and conveyor is cleaned on a strict schedule using a validated multi-step process that includes rinsing, application of food-grade alkaline and acidic detergents, hot water sanitizing, and ATP testing to detect any microbial residues. Cleaning in place systems are used in closed-loop systems like marinade blenders and oil filtration units, ensuring deep sanitation without the need for dismantling complex machinery. Swabs are taken from surfaces and air samples collected to detect airborne pathogens, all analyzed in on-site microbiological labs. If even a trace of Listeria, Salmonella, or E. coli is detected, entire zones of the plant are shut down and sanitized before production can resume. In parallel to these food safety systems, sensory panels and culinary scientists at centralized R&D hubs conduct organoleptic tests to ensure product consistency. These tests assess everything from the crunch of the breading to the juiciness of the meat and the aroma released when the bucket is first opened. Chicken from multiple plants is cooked and compared side by side in blind taste tests to identify deviations in flavor or texture. If a factory's output strays from the baseline profile, its formulations and techniques are reviewed. In some cases, regional adaptations are permitted. For instance, a slightly spicier breading formula in Southeast Asia, or a less salty blend in Scandinavian markets. But these must be approved through corporate sensory panels and extensive pilot runs. Now it's time to take a look at how traceability and supply chain visibility are achieved at scale. Every piece of chicken can be traced through a blockchain-based system that logs data from farm to fryer. RFID tags and barcode labels track each pallet, batch, and case throughout its journey. When a truck departs a cold storage warehouse, its GPS location is monitored in real time, and its refrigeration status is transmitted back to the operations center every 5 minutes. If a delivery truck's temperature rises above the acceptable range for more than 10 minutes, alerts are sent automatically, and corrective actions are triggered, either rerouting to a nearby cold facility or discarding the load, depending on the severity of the excursion. Once the product reaches the restaurant, the store-level staff become the final link in the quality chain. Every team member is trained not just in food preparation, but in safe handling and equipment calibration. They measure oil temperatures with infrared thermometers before every cooking cycle, check holding cabinet thermostats each hour, and perform timed inventory rotations to prevent expired stock from being used. Any discrepancies are flagged in a digital checklist that is reviewed daily by shift supervisors and weekly by regional managers. Corporate auditors also perform unannounced inspections using checklists derived from international food safety certifications such as ISO 22000 and BRC Global Standards. But up next is a growing area of emphasis for KFC's manufacturing process, sustainability. As environmental concerns increasingly shape consumer expectations and regulatory policy, KFC and its supply chain partners have invested heavily in reducing their environmental impact without compromising efficiency or food safety. For instance, many factories now operate on hybrid energy models that integrate solar or wind power into the grid supply. Heat exchangers capture and recycle waste heat from fryers and ovens to preheat water for cleaning cycles. Water treatment plants have been installed adjacent to major facilities to purify and reuse water from scalding tanks and chilling baths, thereby reducing freshwater consumption by up to 60%. Waste management is another cornerstone of sustainable operations. Offcuts, bones, and organ meats removed during the evisceration process are rendered into protein meal for use in animal feed or fertilizer. Oil used during the par-frying phase is filtered multiple times and eventually recycled through third-party processes into biodiesel or industrial lubricants. Even the breading flour that falls off during coating is collected, sifted, and reused within the same batch cycle if it remains uncontaminated thanks to high-speed sifters and air classification systems. Packaging materials are continuously redesigned to reduce plastic use, and many regional markets have adopted compostable or recyclable buckets made from sugarcane fiber or recycled cardboard. Now let's touch on automation and the future of food manufacturing. KFC's supply chain continues to push the boundaries of factory automation. Smart robotics now handle everything from chicken loading and cutting to box folding and pallet stacking. Machine learning algorithms analyze yield patterns, worker performance, and maintenance schedules to optimize output while minimizing downtime. Vision systems are paired with artificial intelligence to assess product quality in real time, not just based on weight and shape, but also by identifying anomalies invisible to the human eye, such as microfractures or uneven breading density. One of the most promising developments is the integration of digital twins, virtual replicas of entire production lines that allow engineers to test modifications in real time before applying them in physical factories. If a new breeding formula is under development, it can be modeled digitally to predict how it will behave under tumbling, par-frying, and freezing conditions. These simulations save weeks of trial and error testing and reduce waste. Some facilities even employ predictive maintenance systems powered by sensors embedded in critical equipment. These sensors monitor vibration, temperature, and pressure, allowing for preemptive repairs before machinery fails, ensuring smooth operations and uninterrupted chicken production. KFC has also begun exploring vertical integration of its logistics chain. In some regions, specially designed micro-factories are situated closer to major urban centers, reducing transit time and carbon emissions. These micro-factories handle final stage breading and par-frying, enabling fresher product delivery and enhanced responsiveness to demand fluctuations. Combined with real-time sales analytics from thousands of KFC restaurants, these decentralized production nodes can respond dynamically, ramping up or down based on foot traffic, promotions, or seasonality. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3-ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture. which allows it to hold up through the unique double frying process that Five Guys uses in-store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 G. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In-store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. Cafe practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under cafe practices, the beans are harvested, typically by hand. Hand-picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, The glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, The sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios.